Okay, so I think we have started the recording. Let me just confirm. Yeah. So, good afternoon, everyone. There was some technical issue with my computer system because of which we got somewhat late today. But, anyways, let's start. So, good afternoon. Uh, as you know, this is the interaction session 4th for the NPTEL course Experimental Physics 2, which is being taken by Professor Amal Kumar Das from IIT Kharagpur. And I am a PMRF Research Scholar, Mrinalini. I'm from School of Physics, University of Hyderabad. And I'll be helping you guys. I'll be taking these interactive sessions for this course where you can ask your doubts. Related to every week, we are having this interactive session before your assignment deadline so that you can clarify your doubts here. So let's start today's session with this. So let's have a quick recap of what all the things we discussed last week so that we know where we are going with this discussions. Last week we had kind of introduction to different kind of components we find in an optical lab, like different kind of mirrors, lenses and other kind of equipments. Then we had studied law of reflection, law of refraction. Then these were the different, oh, these were the equipments we talked about. Then we had discussed various experiments to find out the first we understood these different parts of mirrors and lenses, that there is something called pole, focus, and how parallel rays come and where they reflect. After that we had done this laws of refraction we had done, and we had also solved some questions based on law of reflection and law of refraction. Then we did this experiment where we had to determine focal length of concave mirror, focal length of convex mirror, focal length of convex lens. Okay, so these were the three we did for concave mirror, convex mirror, and convex lens. In this week's lecture, the experiment 4, it was about determination of focal length of a concave lens. So again, I would request for understanding the experiment, I would ask you to go and watch these lectures where the professor has explained, he has demonstrated the whole experiment. And here we will be trying to just understand the theory, and if there is some particular doubt then we can discuss that. And further main focus will be to do some numerical problems so that it will help you in solving your assignment questions, and ultimately of course it will help you in exam for this course if you have enrolled for it. So this experiment was on focal length of a concave lens, and again, just like convex mirror, concave lens also always makes a virtual image which is erect but virtual, and that's why we cannot get this image on a screen. These things we had discussed last week. So to find out the focal length of concave lens here, this concave lens, we are using this convex lens. So like the object is here, if and its image is forming at this point, and if we keep this concave lens in between, which is a diverging lens, then this image behaves like object for it, and the image, second image, final image is formed here. So with this experiment we had to find out focal length of this. You'll better understand from the demonstration. Here let's focus on the numerical based on it. If we have, okay, so this was one, and the another experiment was focal length of convex lens by displacement method. Okay, so this was another technique, and so we had already understood how convex lens focal length we can determine, but there is another method which is called displacement method. In this method, what happens, we have an object needle, and through I mean, what the principle behind this is, if the distance between object and the screen, so here in experiment we have image needle, but in theory we talk about a screen where we can get the image. So if the distance between object and screen is greater than 4 times the focal length, so if the distance between object and needle, let's call it d, if d is more than 4 times the focal length of this convex lens that we are using, in that case we can use this displacement method. In this, what happens is that the image formed at this position, the image will form at this position when we'll keep the lens at two different positions. So position O1 will also give the image here, position O2 will also give the image here, only if the distance between object and the image is more than 4 times the focal length of this convex lens. So let's do little derivation for this to find out how do we get this formula. Okay, so I think maybe we can just understand this. So here the experiment, let's just quickly, this is the screenshot from the lecture itself. So this is the object, okay, this is the object, this is the convex lens kept at some point, and the object is one ray. You remember we take two rays, we consider two rays. One ray going parallel to this convex lens will pass through the focus on the other end, and one ray passing through the pole of this convex lens will go straight, and these two rays where they are meeting, there we will say we are getting our image, which is real and inverted. Now if so, let's call the distance between object and the pole of the convex lens as u, and the distance between image and the pole of the convex lens as v, and the total distance between object and image will be d, which is d is u plus v. Okay, this all we are doing for the case when distance between object and image is more than 4 times the focal length of the convex lens. So when I am moving this convex lens to some other position, okay, such position from where I get the image at the same place, then what happens, this is our lens formula. If you remember, for mirror it's 1 by v plus 1 by u is equal to 1 by f. For lens maker formula, it's 1 by v minus 1 by u equals 1 by f. And then we have to, of course, take care of all the signs according to which lens we are using and at what distance the object is. All these things again we had discussed with every numerical last week. So here if you see what is v, since d is u plus v, so v becomes d minus u. Putting that value here, and as I had said, sign convention when we talked about last time, because sign convention is very important, otherwise we'll be getting wrong values. So when like if this is my mirror or lens or any kind of these component, and ray of light I am considering towards right, then if anything I am measuring in opposite direction to this light, direction of light, if I am measuring anything opposite to the direction of light, then it will get negative sign. If whatever distance I am measuring is in the direction of light, then it will be positive. So here the image is forming on the right, so image v will be positive, whereas the object is on the left side, so it will be negative. That's why this is positive, this is negative, and focal length is on this side, so it is positive. Now when we rearrange it, we'll get this quadratic equation, and after solving this quadratic equation by this, this comes from x square minus ab plus c, that kind of coefficient. When we solve, we get d plus minus under root d square minus 4df by 2, and then we'll get two solutions for this. From this we'll get u1 and u2. Just a minute. Okay, so solving this, when we change this distance, we have to take care. This is u1, u2. Then in terms of this, u1 expression will be this, u2 expression will be this. So from this, basically we find out f is equal to d square minus x square by 4d. Now the another whole lecture was about applications of mirrors and lenses. We have different, like we understood how these mirrors and lenses work, how we are able to do experiments to find out focal length of these mirrors in our labs. But we need to, like, of course, final question is where these things are useful. So we'll talk about applications of mirrors and lenses here. The first application that we can all see even outside any optical lab is human eyes. First, let's talk about human eye. So this here is a schematic representation of a human eye. Okay. Where we have a convex lens inside, and whatever object we see, the light passes through it and it goes to the retina, through which we are able to see it. But there are two conditions when we are not able to see these objects. That happens when we have the conditions called myopia or nearsightedness. In this, what's happening is either something is happening to these lenses or the shape of the eye, because of which the light is not focusing on the retina, from where we have optic nerves connected, and then we can perceive these images. So when we have myopia or nearsightedness, as you can read, we can see here, in this condition the person can see the objects nearby, like from this distance, but for far away objects the image is forming before the retina, and that's why we are seeing it blurred. Just a minute. This is too thin. It's okay. So when this kind of situation happens, we are not able to see, the person is not able to see properly, we use some corrective lenses. Like for this particular situation, we use concave lens. Please remember, concave lens follows all the properties of a convex mirror. Convex mirror, that is, all the images formed are virtual, erect. Yeah. So we use this, and since these concave lenses are diverging in nature, we also call concave lens as diverging lens. Okay. So instead of the light going and focusing here, because we are using a diverging lens before it focuses somewhere here, it diverges the coming beam slightly, so that when it focuses through this convex lens, it focuses at a correct distance, which is slightly more than the point where it was forming because of the problem. So this is the use of concave lens to correct the sight. Another issue happens when it's called hypermetropia or farsightedness. In this, the the person can see objects at a distance but cannot see nearby objects clearly. This in this, what happens is, like you can see here, this is the normal in normal condition. I mean, the near point is closer. So if that the object is closer than their near point, then the image formed is even beyond the retina, and that's why it's blurry for them. They are not able to perceive it properly. This is called hypermetropia condition or farsightedness. The another thing is, correction for this is using these convex lens here. In previous condition we were using concave lens, this which is also diverging lens. Yeah, diverging. Now we are using for this particular condition convex lens, which is converging, which is also called converging lens. So what it does, the rays here were converging at far point, but using this convex lens in between, we are making the rays to converge a little earlier at the correct point, that is at the retina. So this is how we use these lenses to correct the human eye problems. So these are one case of applications. The second application is as in magnifying glass. As you can see here, we use magnifying glass to magnify anything that we want to see. Magnifying glass, usually which glass we use for it is convex lens. For a convex lens, when object distance is less than focal length of convex lens. For convex lens of a concave mirror, we know when our object is kept at a distance less than focal length, then the image formed is virtual, erect and magnified. That's why that is also the reason when we use magnifying glass, we have to hold the lens closer to the object and far from our eyes. If you will keep it away from this object that we want to see, and if it is beyond focal length, then we won't be getting erect image, and that won't be useful. So this is like how we get the working of magnifying glass. Like, consider we have convex lens, and again, as I said, for keeping, like, for magnifying glass to be useful, we have to keep it closer to the object, means the object distance from the lens should be less than the focal length. If our object is at here somewhere, that is less than the focal length distance, then again, considering the two rays that we choose, one ray we will consider going parallel to, for this convex lens there will be this normal where there is pole. One ray going parallel will of course pass through focus on the other side, right? And one ray going through the center of curvature will, this is straight line of course, I am not able to draw this, so yeah, wait, sorry. One ray going parallel to the convex lens converges at focus, another ray going through the center of curvature goes like this, and both are diverging. So if a person sees from here, it seems to them that the object, that the image is forming somewhere here. So this was the object, this is the image, and you know magnification formula is given by image height to object height, or distance of image to from the mirror, from the lens or mirror to distance of object. So this is what happens, and we get the magnification. The third use is in camera, where this is the schematic of very simple camera. Here, because our object distance could be different, thus accordingly we want to set the different, we want to use a lens of different focal length. If we have a particular lens, be it convex lens or concave lens, then they sorry then their focal length is fixed, we cannot change it. But if I'm using combination of two lenses, then depending on the distance between them, if I'll vary the distance between these two lenses, then overall combination of these two, they can have varying range of focal length. And then the total, the focal length of the combination can be given by this formula, where d is the distance between these two lenses. Okay, so based on this the camera works, and other things are as similar to the human eye that are discussed in the lecture, like aperture, which acts like pupil in human eye, where we can control the amount of light entering. So it's like inspired from human eye, but then here we can change, like in human eye we can change the focal length by squinching our eyes, but for here in camera, this is how we can change the focal length. Another use is our we see in microscope and telescope in our labs. A microscope in which we magnify very small objects which are near the objective lens, whereas in telescope we magnify very small object from very far distance. Because we know microscope, I don't know if I have a picture or not. Anyways, that's okay. So for microscope, this is again a very simple diagram where we are using two convex lens, which start from, this is our object which is very small, then because it's kept at very small distance than the focal length, so we get a real inverted image which is magnified, and then when we keep it at the center of curvature of another convex lens, then we get a inverted image again, because this is object for this second convex lens, thus the image formed is inverted with respect to the object, which is again magnified. Now we are keeping one more convex lens for which this is an object, and depending on the distance we are getting virtual erect image here. So you can see this was our initial object, and using the combination of these three convex lenses we are able to get this third image which is erect and many folds magnified. So this is a simple microscope lens combinations. Telescope also, it's well kind of similar, but here we see like out of earth objects, so it's very far from us. For this we use something called Galileo telescope, which is a simple setup of a telescope. We can say here we are using combination of a convex lens and a concave lens. So here why we are showing parallel rays, because the rays are reflecting from a very far away object, so they are almost parallel, but they are not parallel to this parallel axis, but they are parallel and they are falling on this convex lens. And convex lens, as we said, is a kind of converging lens, so they will converge at a point, but before they converge, say if they are converging at this point, and before they converge if we are keeping this diverging lens, concave lens, then instead of converging at this point they will be scattered and seem to be coming from this point, because of which we will get an image here. So this is how the Galileo telescope, the simple mechanism works. There are more applications that we can talk about. This we had discussed in last session also, but here again, because in the lecture it was emphasized. So concave, so till now we were talking about convex lens and concave lens and convex lens. Now again recalling the applications of concave mirror, which is again converging mirror. So concave mirror gives us enlarged image when object is between pole and focus. Again, when it's at distance of less than focal length, then we get erect and enlarged image. So we use it in torches. Why? Because there's a light bulb and around it are the concave mirrors, so that the light gets, parallel light of ray gets placed at focus. This again is like recalling that when the light rays at infinity, the position of image becomes at focus, and as we bring the object nearer and nearer to the concave mirror, the image goes far and far away. And depending on the position from the concave mirror, the kind of image, nature of image changes. So we use it in shaving mirrors and makeup mirrors because when they are kept near the face is within the focus of concave mirror, the uh, we get enlarged, virtual and erect image. That's why we use them in shaving mirrors or makeup mirrors. This is again the same as used by dentists because we get magnified image and erect. They are used in torches and beam lights because lights, as I was saying, light bulb is placed at focus. This produces powerful parallel beam of light. This can be seen at large distance. They are also used in solar furnaces to produce heat, to concentrate heat. Like if light rays are falling and you kept something at the center, as we said for concave mirror, when the lights are coming parallel, they'll get focused at the focus point. So whatever, if I want to cook something or in solar cooker or somewhere, then all the light, parallel light which now are focused, will be more efficient. So these are the very much useful applications of these concave mirrors. Now talking about convex mirrors, they always give erect and virtual images. So that's why we don't use concave mirrors for side mirrors, because depending on the distance, as we said, concave mirrors may give inverted image, which will be a problem. So we use convex mirrors, which may not give the correct size, but it gives erect image always. That's why we use it for rear view mirror or side view mirror, or these traffic mirrors. The same thing here, it's been explained. Convex mirror is used as rear view mirror because image formed is erect and the image produced to the driver is not inverted, diminished, so that we can get in a small area we can see a large view of the background. Okay. So the next experiment was, apart from this finding out focal length, was about determination of refractive index of liquid using traveling microscope. So just to again show how a traveling microscope works is, if we have some sample kept here and we move this traveling microscope where we are able to see it properly, then that distance we measure from here. So that this was used in this particular experiment. Now we'll see how we can find out refractive index of liquid using traveling microscope. So this was basically on this principle that if I have some object kept in water, like I have some water in a container, if I'm keeping, be it some rod or a pencil is kept here, then when I'll see from here, consider this, sorry, consider a person's eye here, when they'll see it to be bent, although, sorry, let me erase it. If it's like, I'll see it like this, even if I'll see it to be bent. Okay, we'll understand why this happens, and based on this only we were able to do this experiment and find out the refractive index of liquid. So if you'll see from here, okay, we'll see this to be bent, although it's going of course straight. So we'll try to understand what's happening here and how the length changes. So if I have a interface. One side we have air whose refractive index we can call mu A. Another side I have water whose refractive index I will denote by mu W. Okay. So here, if I have some object here, I don't know why this is happening. I have some object here that I am calling S. Then if a light ray is entering from here, it will reflect and go back from the same path. Let's call this normal point O. Now if we are seeing from here, we'll see it at the correct position because the light ray is coming back from the same path. Whereas if you'll see it from somewhere here, then what happens is that the light ray will be coming like this, and again we need to say what is the angle of incidence. What is happening? I've changed my pen and tab. I mean this writing pad, that's why this problem is happening. Again I'll get used to it, but okay. So if I'll take normal at this position, then this will be my angle of incidence. Right? And because this is rarer medium, the light will bend away, and this will be angle of refraction. This will also be angle of incidence, right? This was O, let's call this O. So what's happening here is, when you will see from the light ray from this point is going in all directions. If you will see from here, it's going in this direction, coming back in this direction, so everything seems fine. But when we are seeing from this side, then ray of light that is coming in this direction, its angle of incidence, angle of refraction of course will be different because this is rarer medium. And when we'll see from here, our eyes perceive the light coming from here at this point, the straight line. If we'll extend this line, and it will be coming from this point, and this is what we'll perceive is the object position, and thus we see things to be bended, or the position has changed, right? Initially, actual object depth is this OS. Actual depth is OS, whereas apparent, what is appearing to us, apparent depth is OS prime. Apparent depth is OS prime. So from Snell's law, we know when we have two different medium with two different refractive index, then the Snell's law tells us that refractive index of one material, here we have the light is coming from water and going to air, so we'll write first this refractive index of water, sine incidence angle I, and other side where the refraction is is happening is refractive index of air, sine R. Now taking the ratio of these two, we'll get refractive index of water divided by refractive index of air is equal to sine R divided by sine I. Now if the angles are very small, which happens for these cases, in that case we can approximate sine to be equivalent to tan. If angles are very very small, which happens for this case. Now for tan, we know tan is the ratio of perpendicular by base. In any triangle, If I want to take tan of this, that means it's this by this. So here tan of r, this is same as vertically opposite angle. Yeah, so when we have something like this, right, the angle that is formed here, it's same as here. So if I'm considering this is r, then this will be r, and this is r, then this angle will be r. Okay. So tan of r will be in this triangle, in triangle, in right angle triangle S prime O O prime, right? This is forming a right angle triangle, triangle S prime O O prime. If you put tan r will be O O prime divided by O S prime, and in triangle S O O prime, which is this bigger right angle triangle S O O prime, in this tan I will be this O O prime divided by O S. O O prime divided by O S. Now putting it here, we can see O O prime, and what we'll get is O S divided by O S prime. And for air, we know refractive index of air is taken 1. So from this, this will become 1. So we will be left with refractive index of W. This is side information. So we will be left with OS, which is, we had seen, it is actual depth. To the ratio of OS prime, which is apparent depth. Okay, so this is the formula that we got. That apparent depth is actually actual depth divided by refractive index of that medium. So based on this, the experiment was performed. If you want to understand the experiment, so what we were doing there, we just wanted to measure 2-3 kind of different distances, because to find out refractive index of liquid, we need actual depth and apparent depth. Only these two parameters we need to find out refractive index. So in this experiment, what we were doing, we had, in what was demonstrated, remember, we had taken a beaker and made some mark at the bottom, and using this traveling microscope, when we keep the beaker here instead of this glass slab, and we keep the beaker here with a mark at the bottom, I'll see from this traveling microscope at the point where I'll be able to get clear image that distance I'll take as distance of this real distance, or what we say, actual depth, you can call actual depth. I'll get like that, and after that we'll fill water in this, and then now the distance will change. I mean, we won't be able to see the object properly at the same distance, so we'll have to move this traveling microscope closer, and then we'll be able to see clear image. That will be apparent depth distance. We'll get apparent depth from this distance. So this was the experiment, and then you can take the ratio and find out the refractive index. Okay, the next discussion was starting on spectrometer and prism, but this is again going to be more lectures on this thing in coming week. So I think we can discuss later time, but basically spectrometer is something that looks like this. We have a slit plate through which we take any kind of light source. It could be white light, it could be neon, sodium light, which comes through this, then reflects from the prism and comes through this eyepiece, which is my telescope. And there are different adjustments that we need to do. This we can understand when we watch the other lectures next week. Hello. Did someone say something? No, then okay. Just see it's happening properly. Okay. So these spectrometers and prism, how they work, where we use, we'll understand in next session. Let's now do numericals on these refractive index and Snell's law and the convex lens that we have discussed. So the first question is this, that the refractive index of glass and water are respectively 1.5 and 4 by 3. The velocity of light in glass is 2 into 10 to the power 8 meter per second. What will be its velocity in water? The refractive index is given by velocity of light in air to velocity of light in medium. This is how we define a refractive index for the medium. So here we have been given refractive index of glass and water, and we have to find out velocity of light in the glass. So from these two cases, we will refractive index of glass, which is 1.5. That means its velocity of light in air divided by velocity of light in glass. The next condition given is refractive index of water. The refractive index of water value is given to be 4 by 3, which is again the ratio of velocity of light in air, velocity of light in water. From these two equations, if I'll take ratio of them, like I'll divide 1 by 2, then I'll get 1.5 divided by 4 by 3 is equal to, it will be VA by VG divided by VA by VW, which will be VA by VG multiplied by VW by VA. So as a resultant, we will get ratio of VW to VG. Now I need to find out velocity in water, that is unknown, but velocity in glass is known, which is given to be 2 into 10 to the power 8 meter per second. Okay, so velocity of light in water will be 2 into 10 to the power 8 into 1.5 divided by 4 by 3 means 3 by 4. When we solve this, two times 3 times 1.5 divided by 4 is 2.25. It will be 2.25 times 10 to the power 8 meters per second. This will be the velocity of light in water. B is the correct option. Interesting. Okay, so the next question is, a ray of light from air is incident on the plane surface of liquid at 45 degree. Due to refraction, the deviation of the ray is 15 degree. Calculate the refractive index of the liquid. So first let's draw what is the conditions given and what we have to find out. So ray of light from air is incident on the plane surface of liquid. So here on one side I have liquid, on another side we have air. Ray of light is coming, is incident, and it's, as we know, we always take angle of incidence from this normal to the plane or to the surface. So a ray of light from air is incident on the plane surface of liquid at 45 degrees. So angle of incidence is 45 degree. And due to refraction, the deviation of ray, it's not able to follow what incidence of angle is not equal to incidence of refraction. Like we have from Snell's law, refractive index of first medium sin I is equal to refractive index of the another medium where refraction is happening. So here we know it's going from rarer medium to optically denser medium. So the ray of light will, the speed will slow down and it will bend towards the normal. And if we'll extend this incidence light, if for some reason it would be following the direction, then this will be the angle. But it's not following that angle and it's undergoing refraction, and the angle of refraction is less than angle of incidence, which is 45 degree. So here we have been given angle of incidence, which is 45 degree, and the question is saying that due to refraction the deviation of ray is 15 degree. Means if there would not be refraction, the ray light will go in this direction, but there is deviation of 15 degree, and then this is angle R. So we can see here the total angle, which is equal to I, consists of the deviation, which is 15 degree, and the angle of refraction. Right? Calculate the refractive index of the liquid. Now angle of incidence we know 45 degree. So 45 degree minus 15 degree is equal to angle of refraction, that will be 30 degree. So this is angle of refraction. Now we have to find out refractive index of liquid. So refractive index, as I said, of a medium is given by, okay, here velocity is not given, so we'll use Snell's law that I told here. So refractive index where incidence is happening, that is air. So refractive index of air sin I, which is 45 degree, is equal to refractive index where refraction is happening, which is this liquid. So refractive index of liquid and sine of refractive angle, which is 30 degree. So refractive index of air is 1. From this, refractive index of L will be sine 45 degree divided by sine 30 degree. So sine 45, if I see sine 45 is how much? Sine 45 is 1 over root 2, and 1 over root 2's value will be 0.7071. Sine 30 degree, which is half, that will be 0.5. Now the ratio of these two values will give 0.707 1 divided by 0.5, 1.4142, which is the value of actually root 2. Root 2 is equal to 1.412. Or if we did, I think we didn't need to calculate this. Sine 45 degree is 1 over root 2, and sine 30 degree is half. So for this we'll get so root 2, because in option it's given in square root, so this will be the correct answer. Okay. Next question is, a ray of light falls on a glass plate placed fully immersed into water. We have a glass plate which is fully immersed in water, means on this side if I have glass, on opposite side we have water. This is the situation. A ray of light falls on glass plate. Now just let's talk about this interface. One side we have glass, on the other side water, and we are just focusing on the interface where the light will be incident and refract. So light is falling on this glass at angle of incidence 45 degree. Again, this will be the normal. Angle of incidence will be taken from here. This is 45 degree. What is the angle of refraction inside the glass? Of course, water is rarer medium compared to glass. So inside glass, its angle will change. We have to find out what will be the angle of refraction. If refractive index of glass is 1.88, refractive index of glass is given to be 1.88, and refractive index of water is given to be 1.33. We need to find out angle of refraction. So from the Snell's law again, Snell's law, here for our water and glass interface, when we'll apply Snell's law, we'll get where angle of incidence is, so refractive index of that medium, and sine 45 degree, where refraction is happening, which is glass medium. So refractive index of glass and sine of R, which we have to find out, which we don't know yet. So to find out this, sine of R, refractive index of water to refractive index of glass times sine 45 degree. Refractive index of water is 1.33, it's given, divided by refractive index of glass, which is 1.88. Now sine 45 degree is sine 45 0.7071. Then we will calculate all this together. 1.33 multiplied by 0.7071 divided by 1.88. What is 1.33 divided by 1.88? We'll get 0.500. So this is the value of sine of R. Now to find out the refractive angle, we have to take sine inverse of this. Just to find out refractive angle, we'll take sine inverse of 0.5, and that will be this will be 30 degrees. Refractive angle of refraction inside glass will be 30 degrees. Next question is, a monochromatic ray of light of frequency this enters from air into a medium of refractive index 1.5. So we have an interface situation. One side we have air, another side there is some other medium which we have not been told. But for this medium, refractive indexes refractive index of this medium is 1.5 and refractive index for air we know is 1. If monochromatic ray of light is incident from air, this is the number, and from here it will refract. This is angle of incidence, this is angle of refraction. We have to calculate the wavelength of light in this medium. We know that for any light this speed is equal to frequency times wavelength. So if we find out this is c, means speed of light in air, in this medium it will be less. If we denote it by v, then it will be less. And actually frequency of light never changes depending on the medium, okay, because it depends on the nature of source. Frequency of any light source depends on nature of source. So even if the medium is changing, so the velocity of the light will change, and correspondingly one of these parameters has to change, as you can see, but that parameter will be wavelength, but the frequency will remain same for both light traveling in air and light traveling in this other medium. So we have to calculate wavelength of light in the medium. So first we will calculate velocity of light in this medium, and then we will calculate the wavelength. So for this, again from here we'll use this formula, that refractive index is defined as velocity of light in air to velocity of light in the medium. Velocity of light in air is this, 3 times 10 to the power 8 meters per second. Velocity of light in medium we need to find out. 1.5 was given. Okay. From this, velocity of light in this medium will be 3 times 10 to the power 8 divided by 1.5, which will be 2 times 10 to the power 8 meters per second. This will be the velocity of light when it enters in this medium, which we can see clearly is less than the velocity of light that is in the air, because this medium is denser than air. Now we know the velocity of light in this medium, and from this equation we'll find out the wavelength in this medium. So velocity of light is 2 times 10 to the power 8. Frequency we know it's same, so that means frequency is this, 5 times 10 to the power 14, and wavelength we need to find out. So wavelength, this new wavelength, or that is the wavelength in this medium, will be 2 times 10 to the power 8 divided by 5 times 10 to the power 14. And we'll calculate the 2 divided by 5, which is 0.4. 0.4 and 14 minus 8 will be 10 to the power. No, it will be 8 minus 14, it will be 10 to the power minus 6. If I write it in terms of angstrom, then since this is in meters, 1 angstrom is actually 10 to the power minus 10 meters. So when I will convert it into angstrom, it will become, so using this conversion, we'll get this equal to 4000 angstrom. So this is the correct answer. Now this next question is again on refractive index. A rod is immersed partly into water. Refractive index of water is given. Rod is immersed partly into water. So if I have again as the earlier situation, see here is the interface. Here I have air. On the other side we have water. Rod is immersed partly, means half of it, not half, some part of it is in air, some part of it is in water. And refractive index of water is given, which is 4/3. And this is in inclined manner. Now if I make a normal here, okay, this is angle of incidence. This will be, let's see what this will be. For the question is, when observed vertically from above, the rod appears to make angle of 45 degree. When we are seeing exactly from here, okay, the rod appears to make angle of 45 degree with the surface of water. Means the rod is making angle 45 degree with the surface of water when we are watching from here. Calculate the actual inclination of rod with the water surface. Okay, so it's not, they are not watching from here, but just somewhere vertically. So what it appears. So as we had discussed, the apparent depth and actual depth. So the actual angle will be something else, and it seems to be, we have to calculate actual inclination of rod with water surface. And what it appears is this 45 degree. So let's consider, okay, let's make a normal here also. And this is the rod, this AC is a rod, and this point C, oh sorry, it appears to be making 45 degree, but actually it's going somewhere. This is actual, and this 45 degree is what it appears to be making, C prime. Now let's mark this something, O prime and O. Okay. Then for right angle triangle, O prime C prime, O prime C prime. In this, if we will take tan 45 degree, that will be, tan 45 will be perpendicular, which is O prime C prime, and base is O prime, O prime. Similar way, in the right angle triangle, O prime and C, this bigger right angle triangle, in this, tan of the actual angle we have been asked to calculate, whatever is the actual angle. Let's call it theta. So tan theta will be O prime C divided by O prime. Now if I don't know O prime also, so if I'll take ratio of these two equations, I'll be able to rectify this unknown parameter. So when I'll take ratio of 1 and 2, is tan 45 degree, tan, let's take 2 by 1, that will give tan theta divided by tan 45 degree. So it will be O prime C divided by O prime divided by O prime C prime divided by O prime. So this will be cancelled and we will be left with O prime C divided by O prime C prime. Okay. Now, since we know that O prime C is the apparent depth and O prime C is the actual depth, and these things are given as a ratio of refractive index also. So real depth to the ratio of apparent depth is the ratio of refractive indexes. Refractive index of water to refractive index of air, which is actually 4 by 3 divided by 1. So when we keep it here, that means tan theta will become tan 45 degree, and since tan 45 degree is 1, so it will be 4 by 3. Now theta will be tan inverse 4 by 3, which will be 53.130 degrees. So the actual angle will be 53.130 degree, and the apparent angle that we were seeing was 45 degree. This is the correct answer B. The next question is, point source is placed at the bottom of a tank. So again we are talking about water medium. Okay, we have water medium, and then we have a point source placed at bottom of a tank containing water at a depth of 80 centimeter. So this point source is at distance of 80 centimeter, means the actual depth is 80 centimeter. What is the area of surface of water through which light of the source can emerge? So this is some sort of light source. You know, the light coming from this will go straight in this direction, but while going in any other direction it will undergo refraction. So if I consider a light source coming from here, it will be angle of incidence, and it will undergo refraction. Because this is water, this side, and another side it's air, that is rarer medium, so the angle of refraction here will be more than angle of incidence. And the question is, like, the rays of light from this point will go in several directions, and we have to tell area of surface of water through which light of source can emerge. At the interface, what is the area through which the light can emerge? So here we need to understand something called critical angle. We denote it by theta c. So what do we mean by critical angle is when a ray of light is moving from denser medium to a rarer medium. That time this situation happens that this is my angle of incidence, and since it's moving to a rarer medium, it will move away from normal. If my angle of incidence is increased to some I prime value, then this will move even further away to some R prime value, and there will be a situation, there will be some angle of incidence value which we call actually critical angle, at which the refraction will be along the surface. It will be the refraction will be 90 degree. So angle of incidence at which the angle of refraction becomes 90 degree is called critical angle, theta c or IC angle. And if the angle of incidence is even larger than this critical angle, then that refraction will come back into the same surface, and this is called internal reflection, because the incidence light is in the same medium and the reflected light is also coming to the same medium. So this is called internal reflection. So beyond critical angle, if we will go, then the light will not come out, it will go back in. So that's why here we have to consider this critical angle, so that we can tell what is this area through which the light can come out. So after understanding this, what we have to do is, there is a formula of critical angle we use, sine theta c, it will be refractive index of air and refractive index of water. So refractive index of air is 1, refractive index of water is given to be 1.33. Okay. Now sine theta c, here this will be the critical angle. This angle of incidence maximum, it can be I maximum, can be I maximum I maximum can be this theta c. It can be less than it, then only it will come out, but it cannot be more than theta c. So I maximum can be theta c, because we need to find out this area. And considering this right angle triangle, we'll see sine theta c is A. Okay, let's mark this A, this let's call it B. What is the problem here? I don't understand. This is B. Seriously? This point is B. Yeah, keep on doing this. And this is O. Okay. So AB divided by BO. This is basically what AB, let's call it some radius of this area, X. So X, and BO is, so if this is 80 centimeter, but let's for convenience call it H. Okay, this is X, then this will be square root, because it's a right angle triangle, so the hypotenuse will be H square plus X square. So this was the this is the formula that we get, that critical angle, how we find out for this particular two medium interface, that is refractive index of air to refractive index of water. Now for sine theta c in this right angle triangle ABO, AB by BO will be sine theta c, and that will be equal to x over under root H square plus X square. Now this is 1 over 1.33, or for convenience let's just write it as 1 over mu of water. Okay, now we have to solve it. So this will be equal to 1 over mu W. We want to find out what, from this we want to find out this X, because we have to tell what is the area of water through which the light will come. So I want to find out, this will be a circle because it's forming cone in all directions, and if I know the radius of the circle, I'll be able to tell the surface area. So I want to find out X out of it. For that, I'll take square on both sides, then I'll get X square divided by H square plus X square is equal to 1 over mu W square. I'll take one more slide. see recording is happening fine. Okay. So taking this equation, solving this further, I'll take reciprocal on both sides. Then I'll get x square plus x square divided by x square is equal to mu omega square. Yeah, reciprocal of this. Now when I'll divide by x square, we'll get x square plus x square plus 1 is equal to mu omega square, which implies h square by x square is equal to mu omega square minus 1. Right? Now this is also not finished. Now from this, when because I want to find out x square, so I'll send x square this side, or I can just take reciprocal. So x square over x square will be 1 over mu omega square minus 1. That means x square will be h square divided by mu w square minus 1. Now h, I know it was what? H was this actual length of this point source, which was 80 centimeter. So 8 square of that, and mu omega w, which is refractive index of water, which is 1.33. 1.33 square of it minus 1. And we'll solve this. Okay, so this is x square. Now for area of required surface, for our question, it will be pi x square, pi 22.7, and x square is this value, 80 square divided by 1.33 square minus 1, and we'll solve. It will be, let me solve this. This will be 80 multiplied by 8. 6400 divided by what this will be. This will be 1.33 minus 1 and 1.33 plus 1, right? Because a plus b, a minus b is a square minus b square. So from this 6400, this will be 0.33 multiplied by 2.33. That means 0.33 multiplied by 2.33. It is 0.7689. 0.7689. And I'll divide 600 divided by 0.7689. I'll get and there is, sorry, I forgot this, pi is there, so I'll get So I'll get 26159.82. This is centimeter square because the height was in centimeter. So option A is the, I think this should be 261. I'm getting 5 here. If you guys are getting something else, then let me know. This is the answer matching to me. If it's 5, let me know if there is some mistake. Otherwise, this is the answer. Okay, so the next question is, these were now all on refractive index. Now the remaining questions are on converging lens, I think. So when an object is placed at a distance of 30 cm from a convex lens, this is principal focus, this is convex lens. Object is placed at distance of, say here, object is there and this distance is 30 cm. Okay. Real image is formed at a distance of 60 centimeter from the lens. Real image is formed, it will be on the other side and it will be inverted. One ray going parallel to the principal axis, it will go through the focus. Another ray going through center, this will go again here, and the image will be formed real inverted, maybe magnified. So image is forming at 60 centimeter. Okay, you have to find out focal length of lens. So for lens, the lens maker formula is, which tells us the relation between object distance, image distance, and focal length of our optical material, which is lens, convex lens here. So the formula is 1 over v minus 1 over u is equal to 1 over f, where u is the object distance, v is the image distance. Now this is the formula, but first for this particular condition we need to find out the sign convention. So here the object is on the left, so u will be negative, image is on another side, so image will be positive and focal length will be positive here. So taking these into this, our lens maker formula modifies and becomes 1 over v plus 1 over u is equal to 1 over f. Substituting the values, v is 60, u is 30, and I need to find out focal length. So this will be 60 to will be 3 by 60 is equal to 1 over f. That means f is 60 by 3, that is 20 centimeter. So the focal length of this convex lens is 20 centimeter. Next question is, when an object is placed at 12 centimeter in front of a convex lens. Again a convex lens. Object is placed 12 centimeter. When we are talking about the distance, we take this, okay, the pole is here, right? So from there we are talking about. Object is placed 12 centimeter in front of a convex lens, 4 times magnified virtual image is formed. So virtual image is only formed when the object is placed at a distance less than the focal length, we know that. And virtual image is formed on the same side. This also we know about convex lens. So if object was here, then image will be somewhere here. It will be magnified, it will be erect, it will be virtual. In this case, the parallel ray going from this object will pass through the focus. Okay. From this pole, the ray will be going, and they appear to meet at this side. So this is where we see image. Okay. So now for this situation, u will be negative and image is also forming this side, so it will be also negative, and focal length, which is here, will be positive. So lens maker formula, which is actually this, after considering sign convention, it will become 1 minus v plus 1 over u is equal to 1 over f. In this, when we will substitute the values, what we know here is object distance, which is 12 centimeter, and we have been told that virtual image is formed, which is 4 times magnified. So for magnification, we know magnification is, if we consider image height is h prime and object height is x, then magnification is given by height of image to height of object, or it's also given by the ratio of distance of image from the pole to distance of object from the pole. So heights we don't know, but we know the object distance, and magnification is also given, which is 4 times. That means the image distance is 4 times the object distance. Object distance is 12 centimeter. So image distance is 48 centimeter. This information I can substitute here. So minus 1 over 48 plus 1 over u, 1 over 12 is equal to 1 over f. So this will be 12 minus 1, 4 is equal to 1 over f. This means f is 12 divided by 3, which is 4 centimeter. Oh sorry, what happened? Sorry, this is 48. This is 48. When we'll take LCM of 48 and 12, it will be 48. This will be 48. So the answer will be 16 centimeter. 16 centimeter. Yeah, we have to be careful with the calculation, but the concept also is equally important, because this is our lens. We have been given here, we have to apply many things simultaneously. That this magnification formula, then in lens maker formula, the most important thing is sign convention, and then the calculation, for which we can always use the calculator, so that's not a big deal. Next question is, when an object is placed at 20 centimeter in front of a convex lens, its 3 times magnified inverted image is formed. In which direction and how much should the lens be shifted in front of the object so that its 3 times magnified erect image may be seen? So here there are actually 2 situations or 2 cases we need to understand. We have a convex lens. Okay, for case 1, object is placed 20 centimeter in front of convex lens, and we get magnified inverted image is forming. Okay, we are getting magnified inverted image, means real image we are getting, which is 3 times magnified. This distance is 20 centimeter and magnification is 3 times, which again is the ratio of v by u, right? This is u and this is image distance v. It implies that image distance is 3 times u, which is 20 means 60 centimeter. Now this is one case. For second case, the question is asking that in which direction and how much should the lens be shifted in front of the object, means towards the object. How much should let's call it A. The object is fixed at A point. Okay, but the question is saying to shift this lens towards the object, so that earlier the distance was u, now the distance will be some u prime, which is u minus, let's say, some x. So how much the distance x we should move so that the magnified erect image can be seen. We know if convex lens is forming erect image, that will be formed here, that will be magnified, that will be virtual. How much we have to move it so that we get this. That happens when we are less than focal length, right? But here we have to tell how much it is. So this was the image distance. Now this will be the image distance. What this image distance will be, that also we need to tell. And that they are saying how much should we shift so that the object is 3 times magnified. Here, so if the magnification they are saying has to be 3 times, again v prime divided by u prime, it implies that v prime is 3 times u prime and u prime is u minus x. Okay, u I know, if I find out x, then I can tell this. First I can find this all out from lens maker formula, but I need one thing, because we have not been told focal length. So from this case where I know object distance also and image distance also, I'll try to find out focal length from here, and then I'll substitute that value to this case 2. Okay, so let's first from case 1, what will be the sign convention? U is negative. Let me write here, U is negative, V is positive, and focal length is positive as well. So the lens maker formula will be, which is 1 over V minus 1 over U is equal to 1 over F. Okay, after considering sign convention, it will be 1 over U plus, because U is negative, so it will become plus 1 over U is equal to 1 over F. Now 1 over V, V is what? 60. 1 over 60, U is 20, U is 20 for case 1. 1 over 20 is equal to 1 over F. Now solving it further, for which I need one more slide. Let me take that slide. Okay, when I'll solve this further, I'll get 60, it will be 1, and this will be 3 is equal to 1 by F, which implies F, after taking reciprocal on both sides, F will be 60 divided by 4, it will be 15 centimeters. So this is the focal length, and for both cases, because the lens is same, so focal length is going to be same. So now I'll use for second case. For second case, this is object and this is image. So that means for second case, U is negative, V is also negative, and focal length is positive. Okay. So putting this in lens maker formula for case 2, the lens maker formula, which is 1 by V minus 1 by U is equal to 1 by F. From sign convention, it will be 1 over minus V plus 1 over U is equal to 1 over F. Because U and V are negative, F is positive. Now substituting the values, so V is, from here you can see that V is actually V prime, these are all prime, these are prime, because this is for case 2, the distances are different. So with the focal length is same. So V prime is actually 3U prime, which is 3U minus x, 3U minus x plus 1 over U prime is how much? U prime is U minus x. U minus x is equal to 1 over f, that is 15. Okay. Now U was how much? Because U is the parameter from first case. U was 20 centimeter. Put it right on this side. That means 1 over 15 plus 1 over 3, U is 20 minus x we need to find out, is equal to 1 over 20 minus x. Solving this, I think I should have taken it that side would have been better, like 15 over 15 and this is not a good idea. Let me keep this as it is, then it will be, LCM will be 3 times U minus x minus 1 plus 3 is equal to 1 by 15. This will be minus 4 is equal to 3 times U minus x, and 15 also, if I take this side, it will be this. This will be minus 60 divided by 3 is equal to U minus x. that means minus 20. It implies that x is u plus 20. U plus 20 is u, I know is, I'm sorry, what happened here? This u value, why didn't I put? Wait a second. This will be minus 60 by 3 is equal to u minus x, which is minus 20. Is there some problem here? No, this is fine. This is also fine. When we'll take LCM, we'll get this. 3 minus 1 is 2. 3 minus 1 is 2. So it will be 30. So it will be 30. So it will be minus 10. That means x will be u plus 10. And u is 20. So 20 plus 10 will be, is this correct? U is x minus 10. X is u plus 10. Now is there further any mistake? This will be minus 30 divided by 3 u minus x minus 10, 20 minus x. I want to find out value of x. So x will be 10. Why am I getting x is equal to? Is this correct or we are making some mistake somewhere? 3 minus 1 is 2. 30. I don't know what is the mistake happening here. But the answer should be, okay, let me try again this. The probable answers are, okay, let me try again. Again means from, okay, let's start from here. 1 over minus u prime plus 1 over prime. This is correct. This is the sign convention. In sign convention, u is negative, v is negative because they are on the same side, f is positive. So this will become negative, this will become positive, and this is correct. Minus 1 over v prime plus 1 over u prime is equal to 1 over f for the case 2. For case 2. Now, here v prime is 3 times u minus x. 3 times u minus x. U prime is u minus x. And f is 15 centimeter. Putting all these information in this lens maker formula, we will get minus 1 over 3 u minus x. And u, this u we know is 20 centimeter. Okay, so this is u minus x is equal to 1 over 15. Now I'll substitute value of u also, minus 1 over 3 times 20 minus x. Even if I don't do keep it u also, there should not be a problem. U minus x, if I'm taking LCM here, right, it will be 3 times u minus x. This will be minus 1 and this will be 3 times 1. Okay, then it will be 1 by 15, which 3 minus 1 is 2. and this will be u is 20 minus x. Okay, from this I need to find out x, which implies if I take reciprocal, 15 is equal to 3 times 20 minus x divided by 15 is equal to 3 times 20 minus x divided by 2. If I take 2 on the left side, it will be 30, right? And this 3 in the division when it will come, then it will be 10, 20 minus x. And from here, x I will take left side, then it will be 20 minus 10. It will be 10 centimeter, which is the correct answer. I don't know, maybe some sign mistake we are making here. Something we were doing wrong. This is minus 2 by 50 minus 30 by 3. There's some sign issue was happening. So the correct answer is that when this x was the distance by which we are moving the lens towards the object. So if we move 10 centimeter towards the object, the lens, then we'll get virtual erect image which is magnified and it will be on the same side. So the correct answer or correct option is B. Okay. Now the next question is a concave lens here. Now we are talking about, which is a diverging lens. Concave lens of focal length 15 centimeter. Okay, focal length is given. Is placed on the path of a convergent beam. Let's draw principal axis. Some convergent beam is coming here. Okay, some convergent beam was coming. And it will converge at some point. If nothing comes in between, it will converge at this point, say P. Okay, but if we put this divergent beam in between, so this was the situation. Now I am keeping a divergent beam here. So this diverging lens here, which is a concave lens. So the beam was converging at point P. Now because of this divergent beam, they will diverge little bit. Okay, so initial was going here, now they will diverge, but divergent doesn't mean this very large angle divergent. Maybe it was coming like this, and now from this normal, they will diverge slightly. From this side also they will diverge slightly and thus they will again meet, but now they will meet at a little more distance. Let's call this P prime. So the point of convergence is at a distance of 3 centimeter from the lens. So this distance of point of convergence was 3 centimeter. Where will the rays converge after refraction? Initial convergence distance was 3 centimeter. Now because I introduced a diverging lens, which is concave lens, then these will diverge and converge at a higher distance, farther distance. And what is that distance? We need to find out. So the thing is here, this OP let's call it OP. This OP becomes object for this concave lens, and the image is forming at OP prime. So this becomes object distance for concave lens, and this becomes image distance for concave lens. In this sign convention, U will be positive, V will be positive, and focal length will be negative for concave lens. Okay. So here U is 3 centimeters. So using our lens maker formula, V positive, U positive, F is negative. If we include this will be our lens maker formula for this situation. Now substituting the values, V I need to find out. U I know that is 15 centimeter, and focal length, no sorry, distance, U is 3 centimeter, focal length is 15 centimeter. Okay, so 1 over V will be minus 1 over 15 plus 1 over 3. LCM will be 15, it will be minus 1, this will be 15. 5 minus 1 is 4, 4 by 15. It implies that V is 15 by 4. Now how much is 15 by 4? 15 divided by 4 is 3.75. 3.75 centimeter. This is 3.75 centimeter along the same side of convergent beam of original beam. This is the correct answer. Okay, so only these many questions we had for this. So we basically discussed refractive index again here, and then did questions based on this. Next class, next week will be based on spectrometer and how we use it. So okay, thank you. I'll stop this.